in the class for record. Right, we continue to look at one tutorial question. All right, so if you look at your tutorial question, question 20, you are given a plate, two plate, and then there's something happen in the middle here, and the axis given is y and x, and the upper plate here is moving in a velocity of 0.3 meter per second. The distance given is 0.3 mm d. So the question mentioned that you are having an infinite plane, it is a very long plane, and we assume we have a linear velocity distribution in a liquid. Liquid viscosity is given. It's given in a non-standard unit, which is 0.65 centipoise, and its specific gravity is 0.88. So this medium is not a normal medium, it's a special medium. So we need to do calculation. So there are four things that we need to solve in this question. So the first one is absolute velocity, viscosity or dynamic viscosity of the liquid in term of, or in the unit of pound second feet square. So although we are focusing on unit SI, but this tutorial intend to guide you through what happens if you need to deal with English unit or British unit, right? The second one, deal with kinematic viscosity, shear stress of the upper plate here, shear stress at lower plate here, each one in a different unit, and the direction that we need to draw up depending on the answer we solve in C and D. All right. Now the first one, okay, before you solve this question, again, you need to download Appendix E. The name is Appendix E Matson because I download this one from the book published by Matson. So Appendix E, you download, then we start to solve this question. Okay. Now again, we recall back the 9 steps that we learned. First, write out all the parameters given in the question. So we have mu, dynamic viscosity, equal to 0.5 centipoise or Cp, and the specific gravity is 0.8. The next one is to find all these parameters. All right. So we try to solve. What are the equations that we're going to use? The equation of shear stress and the relationship with the shear rate here. Shear stress equal to viscosity times the shear rate, and the ratio here given in this form equal to mu divided by rho here. Okay. Now assumption. Okay, so this one, this symbol is kinematic viscosity. Yeah? This symbol is kinematic viscosity given by mu divided by rho. So what is kinematic viscosity? If you look at Appendix A, so if you look at the screen now, you will see dynamic viscosity mu, kinematic viscosity, this symbol, in the unit of meter square of second, because the question asks us to solve this one also. Okay, so another new equation to learn today, a simple equation, kinematic viscosity given by, you take the mu or your dynamic viscosity divided by the density. We assume that the fluid act linearly, and we have a steady flow, and our mu is constant throughout the medium. Okay, now the first one. We will try to convert what is centipoise or CP in pounds dot second over feet square. We try to do conversion now using appendix that you download from Moodle. So the next step is we need to refer to appendix E, table E9. You open up document appendix E, or you already print out. It's quite a lot of page, so you just open the document appendix E, go to table E9. With this you will see on the screen. Right, try to find this table, because in exam this table would not be given. It will be on your own, so you need to know where to find all this value. So for this example, you look for table E9, because table E9, appendix E, table 9, because the table already give you the title. The table is intended to find viscosity, and it's absolute viscosity. So in our case, we are given 0.56 cp. So 0.56 cp. So at this moment, at least at this moment, you know that in your hand you have appendix E, table E.9, and then you are seeing the exact table that I show you on the screen now. So once you find the table, and then you can minimize the document, and then you focus on the screen. At least you know where to find that document, and then you can find later on. Now I want you to focus on the screen. So on the screen here, you will see the table E9 on the left hand side, and then the question asks us to solve our viscosity equal to 0.65 cp centipoise, and on the diagram here you will see centipoise. So we need to convert in pounds dot s over feet square. So it's quite direct how to use this table. You go and find the related information. In this one, centipoise, and then you go to pound second over feet square. So some textbook they put in the unit IBF, means is referring to feet a dimension, but it can be short form become IB.S over feet square. So that just let you know. So there are two kind of notation. So sometimes you will see IBF means pound referring to feet, but you can omit the F when you write the unit. So in this case, we are referring to intersection point of centipoise and pound, like what you see on the screen here. And intersection location is here. You will see it's equal to 4.78 E4 centipoise over pound second over feet. So in all the handbook or appendix or handbook, when you see E4, E4 means 10 power 4. The wording capital E means power. Okay, 4.78 10 power 4 centipoise over pound second feet square. So on your paper, you write this value out. So 4.788 E4 centipoise over pound second feet square. Again, E is 10 power 4. So any question on this table before I change the slides?
No, sir.
Clear?
So, sir, it's
yes.
That means for each pound per each pound times second per feet square equal 4.788 E4 centipoise. Yeah.
Okay, so I'm going to explain what is this number mean to you. It means 4.788 10 power 4 centipoise equal to 1. Equal to 1 pound second. Yes.
Okay.
Because it is taking centipoise divided by pound.
Yeah, okay.
Yeah. Okay, so now we're going to do conversion now. So from the table, you get 4.788 E4 centipoise over pound second over feet square. So it just means that, 4.88 10 power 4 centipoise equal to 1 pound over second per feet. But we are giving in centipoise, so we do the conversion. So we intend to find what 1 centipoise equal to how many pound over second over feet square. That's why in our calculation, we divide 1 over 4.788 times 10 power 4 on the right hand side. Any question before we move on? Anything?
I think Ku is asking a question.
Yeah. Okay. So it means if you take this information, 788 10 power 4 CP equal to 1 pound second feet square. So because the question asks us, give us in CP, so it's more easier for us to do conversion in 1 CP. So 1 CP, you 1 over something, 4 point something to do the conversion. Okay. Then you just times the value, you will get 1.357 10 power negative 5 pound second over feet square, or you can write pound F dot S over feet square. Okay, now for this module, your answer, give me maximum 3 decimal place, minimum 2 decimal place. So 3 decimal place maximum, minimum 2 decimal place. Of course, if you have an index value 10, then this one you need to write lah. Okay, I'm talking about the number in front of all the formula, all the index. Okay, so stop me if you not understand what we're doing now. Stop me if you're not able to understand why suddenly we get 1.36 10 power 4. Yeah,
Sir?
Yes.
I think Ku has a question.
Yeah.
There's a question in chat.
Okay. Yeah, how to know how or you don't understand the table, how to know, find the calculate suitable for that. Oh, okay. It's very direct. So for example, it asks you about viscosity and you're given pound over second per feet square and you're given CP centipoise and you need to convert to other dimension. So what you do is that you go to the appendix. For example, in this case, you go to appendix E, there's a table there, and you know that you are dealing with viscosity. Then you go to table viscosity, and you will see centipoise. Because centipoise is only for viscosity. So it doesn't run off all this on the table. These are all the standard conversion. So that's why you go to table E9. So for example, on this page, you will see table E.10, means appendix E, table 10. You see this one is kinematic viscosity conversion factor. So this one is centi-stroke, it's not centipoise. So centi-stroke is on kinematic. So you don't refer, you won't go wrong one. So it's a one-to-one conversion. Means the dimension you see here, you won't see in other table also. It's only specific for that particular parameter. Okay, let me see what cool. Right? Okay, I assume I answer your question, Aku. All right, we move on forward. The second one, it asks you on B, it asks you to find kinematics viscosity in meter per second. So in meaning, you know the relationship of kinematic viscosity given by mu divided by rho. Mu divided by rho. Let me check the text. Okay, good. Mu divided by rho, because just now in section A, you get in imperial unit. So now you convert back to unit SI. So again, but before you convert, you need to do conversion first. So here we convert the rho, because just now in section A we don't have the rho. We don't even touch on the rho on the density dimension. So for B, you need to calculate the rho for this medium, because this medium is not water. It's not a standard medium. So you need to find. And there's a reason why it gives you specific gravity, 0.88 there. So you just convert, use the information of SG, convert to the density of this medium. So the conversion is rho equal to S. I would say I start with the definition of SG. Rho of that medium divided by compared to the water. Okay, this is the definition we learned last lecture. So we just convert, pull this equation into here, and then you substitute. So Sg times the rho of water. Okay. So mu we defined just now is about 1.36 10 power 5 in pound second over feet square. So our water here, we need to find what is the density of water in the same dimension here also. So the next table we're going to look at is Appendix A. If you have the file Appendix A, open document Appendix A, look for table number 8, A8. Okay, I'm going to show you the table. So open a document, Appendix A, go and look for table A.8, means table number 8, property of water. So in this case, we will use 15 degrees C for this example. For this example, we assume standard temperature is 15 degrees C. So we focus on this density value, 0.99. 0.99. The unit that we use in table A8 is kilogram over meter square. So you copy this value, 999 kilogram over meter cube. Why we use this value? Because we assume that this medium is behaving at 15 degrees C, standard temperature. Okay, so you pull back the answer to the answering table. Okay, you put inside there. The next one is we want to convert the imperial unit into the unit SI that we see here. Okay, all these are constant values, so you can times using your calculator first, then later you do conversion on the unit also can, but you can leave it like this also can. So the next one, so my case is that I reduce all the numbers in one number, so I'll get imperial unit on top, unit SI at below, then I do conversion. So how to do conversion? Go back to table E, Appendix E, table 9 that we see just now, table 8. just below table 9. So flip to Appendix E, look for table E9. Table E9, it will tell you it's a kinematics because section B is referring to kinematics viscosity. So it's quite straightforward. So just now we are using E9, we are using E9, but we are using E9 also. So yeah, so because we are converting into kilogram over meter second, all right, because if you look at the slides here, on top is pound dot second dot feet square. There's a square missing in my slides, and kilogram over meter square, meter cube. So you refer to the table. So in here, you look for the two unit that you're looking for. One is kilogram over second. One is pound second over feet square. You look at the junction of these two row and column. You get this one. Okay, you get this one. Copy this number to the left or to the right, and then you do the conversion. So this is a number that link these two units together. So you have 47.88 kilogram over meter second divided by pound second feet square. Okay, then you pull this number back to the drawing board. Okay, so because we are going to convert pound second feet into kilogram, so we will use this conversion. Okay, so we pull this conversion back to the drawing board, and then you just times the number, because this one is pound second over feet. So sorry, typo error here. So it's over feet square, and then you just time lah. So this number equal to how many kilogram of meter second. So you just times, and then you get your answer in meter square over second. Why you get meter square over second? You cancel out kilogram here, and you move your meter cube up there. You cancel, this one become 2, so you get meter square over second. Question in the chat room. Okay, Ku asks, we have how many appendix table for our exam? So you will know when you come to exam. I will keep uploading appendix on the Moodle. So basically, all the appendix that I upload in the miscellaneous or reference material section, we will be used that for our exam. So you don't need to print out. You actually you keep the soft copy. Okay, yeah. Because the skill that we're trying to evaluate you is the ability to find information. That is more important to us, rather than memorizing the formula or memorizing a certain numbers. So because when you go to work, nobody expect you to memorize a certain number. Okay, they expect you to know where to find information. Okay, we're done for B. Okay, we need to go a bit faster. So for section C, and section C is in imperial unit again, pound second over feet square. So we need to analyze for the upper layer. So we just write the formula, shear yx upper equal to the formula we have, mu over du over dy. So because the velocity is linearly with our y, so we can write something like that. We can write du over dy equal to del u over del y. Del u over del y. So what mean by del u means we take the velocity at the end minus the beginning velocity divided by the distance of our end minus the reference distance. So we have U minus D, U minus D. So we put into calculation. U is 0.3 meter per second. D is, again, a trick in exam. I will give you mm. You need to convert in unit SI, which is in meter, to match the dimension. So you need to change 0.3 into meter. You'll get 0.0003 meter. Again, this error or forget to change unit, this mistake is repeated almost every semester. There will be at least one student who fall into this trap. So take note. Even I remind them, but they still doing the same thing. Okay, so you get what is your du dy value in a unit of 1/second. You continue with the calculation. So previously your mu in pound second over feet square. So 1.36 I already simplified because just now we have 3 decimal. I just simplified. And then you times the number that you get just now, 1000/second. You remove the second. You only have pound over feet square. Then you get the answer already. Anyone text me? Okay. Okay, we clear C. Then we go for D. D, we refer to the value we get from section C. Section C we get for upper is 1.6, 10 power negative 2 pound over feet square. So lower will get the same magnitude also, because we are having a Newtonian fluid here, and because it say that we have a linear velocity distribution here. So the magnitude for shear lower plate here will be the same, because what will move here, it will move here. Okay, I'm drawing the arrow here. So if the first plate will move here, there's a counterbalance action happen. Okay, now again, you need to put in Pascal. What is Pascal? Pascal is again Newton meter square. Pascal is force divided by area. Pascal is a pressure. Pressure is a force acting on a surface. So you want to convert it again. In this time, you are converting a shear. So you flip to Appendix E, refer to table number 7. Okay, Appendix E, table number 7, which give you pressure conversion factor. Why pressure conversion factor? Because Pascal is a pressure dimension. So you're referring to Appendix E, table 7. Okay, so at this stage, you should know where to find all this information. All right, Appendix E, table 7. At least you flip through, you know where to get the information. Yeah. So again, from the table, try to find out the similar dimension that you see in the question. We're going to find Pascal, PA. Pascal, the extension name is PASCAL, Pascal, in Newton over meter square. Another one is in PSI, which is pound per second. Pound per second. Pound per second. So you see this one is pound over feet square. So we slowly change the unit first. So from here, we get the intersection point. We get 6.8 something. E3, again, E is 10 power 3. E is 10, so E3 is 10 power 3. Pascal over PSI, pound per second. Pound pound per square inch. Sorry, pound per square inch. Pound per square inch. So we get this conversion. So we need to put it back. Need to put it back. And then another table we are referring to is area conversion factor, referring to table E number 3, which is in square, because pound as PSI is pound per inch square. PSI is a square inch. So it's a pound over inch. Pound is IB. Okay. So you look at the diagram here, we need to convert inch into feet. Why we look inch in feet? Because the question gives us so. The question gives us in a dimension of feet square here. So that's why we need to eliminate all the related dimension. So here you will get 144 inch square over feet square, means 144 inch square equal to 1 feet square. So you do conversion. Okay, you do conversion. So I'm doing calculation on the screen here. So just now you get 6.895 Pascal, 10 power 3 Pascal. You at the end you will get equal to 144 pounds over feet square. From the table just now you get 1 PSI. PSI means pound per inch square. So you do conversion on the inch to feet, because we want to use this number in our question. So you will get this relationship, 9.8 10 power 3 equal to 144 pound per feet. Then you rearrange according to the conversion that you need. We need is 1 pound over feet square equal to how many Pascal? Because at the end we need to convert into Pascal. So you get 4.78 equal to Pascal equal to 1 pound over feet square. You put this number back to the drawing board. Okay, you convert pound over feet square into Pascal by the conversion that we did just now. You times the answer, you get Pascal. Any questions so far? Any question for this conversion? Yeah, try to get familiar with the material you have. Okay, number E is just drawing on the stress. So the direction of the stress will be opposite of the velocity. Again, I repeat, the direction of the shear will be opposite of the velocity. So the plate moving into the right. So to resist the movement, there's a shear component to the left, and this one you label as shear upper. And to counter the upper, the direction of the shear lower will go to the right. Okay, at least you make sense. Why this one to the left? Because the direction follow, it react to the direction of the upper plate here that move to the right. Okay, just add on information. If the plate going to the right, and you draw shear like that, it means your shear value equals 0. Means there's no shear. Mean that there's no force, there's no resistant force between the medium or the fluid and the contact surface. Yeah, so be careful. So this is add-on engineering notation. Okay, this is just a explanation on this one. So why is negative, why is positive? You read from the slides. Okay, so we continue for non-Newtonian next week, next lecture. Okay, let me stop the recording.